Now that we've looked at how to find probability using the z-curve, now we're ready to explore the most important part of the probability section, which is the central theorem for everything that we're going to look at from here and beyond. And this is called the central limit theorem. This is tied to, again, analyzing the probability of distributions that tend to fall into many different types of distributions. And so what we first want to look at is the law of large numbers. If we're trying to estimate and find a population parameter, remember population parameters are numbers that are associated with large groups. We call those from a population parameters. If we could, many times we would just choose to do a census, but there are many times where a census is not possible. Censuses are very difficult to do over large sections of the population, and in fact sometimes they're just darn near impossible. Samples tend to be less expensive and can ironically sometimes give us actual better numbers or a better picture of how our numbers look for a large group of people. So it provides an estimate, but that estimate, we can actually look at how accurate it is, and we'll actually find that the estimates are pretty darn accurate. But of course, one of the ways we can always increase, and this is something to keep in mind as we go throughout the section, the accuracy of our estimates is to make sure our samples are large enough size. We're also going to look at some formulas that allow us to do that in the near future. So, one sample, if we go out into a population, take one sample, most likely that sample, or that, let's say we're pulling a mean about a population from a sample, you would probably agree that the mean of that sample is probably not going to be equal to the mean of the population. For example, let's just take our last test. If I were to take 5 random test scores from that list of scores, and I found the mean of those 5 scores, and compared it to the actual mean of the test scores, most likely the it's going to be different, because that only represents the mean of that sample of 5. However, let's say I did that 10 different times, and each time I took a sample of 5 and calculated the mean and repeated that many times, 10 times. And then let's take those 10 sample means that I pulled, and let's take the average of those means. What we start to see is that the mean of those 10 means is probably much closer to the mean of my population than any one of those individual 10 samples were that I took. To really get a picture of this idea, we can kind of look at that, it makes sense, kind of see how the numbers might work out. But let's actually look at a population, let's make it small enough that we could really do some analysis with this. So let's take a distribution. We know that a sample distribution, a table, will give us all the possible means for a given sample of size n. So we're going to make our samples small enough that we can really do some analysis on this. So here is 5 basketball players and their corresponding heights. Since we have such a small sample, such a small population really, it's easier for us to just calculate the population parameter, or the population mean, which in this case is simply adding those 5 heights up and dividing by 5. And we see that the mean of this population, the population parameter, is 80 inches. Let's say we take a list of every possible sample size 2 I can grab from this population. When we do that, we can actually compile that list. It's small enough that we can still look at it. One thing I want you to notice is that the list of samples of size 2, and here we went through and we found every possible sample. So we went from AB to AC to AD to AE, and then we went to BC and BD and BE. And we went down and we found every possible sample. In fact, what we actually see is that I have more samples than I actually have members of the population. But let's set that aside for now. Alright, so for each of these two heights, I find the average. You can see that these are all my averages. Out of all of these, you can see that only one of them actually hit the mean on the head of 80 centimeters, or 80 inches, but they're all pretty close around that value. In fact, these values are a lot closer than the individual values I have to the mean. So we have a lot less spread here with these numbers. To the lower end, we're about 3 inches off, and to the upper end, we're about 3.5 inches off. Now, what's interesting is if I take all of these numbers, and remember this represents the every possible sample of my population, you see that the mean of all these means is actually also equal to 80. You can pause this right now and add those up. Prove that to yourself. Add these up, divide by 10. I believe it's 10. 1, 2, 3, 4, 6, 7, 8, 10 values. And see that this actually is equal to the population mean as well. This is an important concept, and it's the first part of the central limit theorem. Central limit theorem actually has 3 main points to it. This is one of them. And here's what it says. For samples of size n, the mean of the variable x bar equals the mean of the variable under consideration. That's a real wordy way to just point out what we just looked at. And symbolically, let's interpret this. We know that the symbol mu means that we've taken, this is representing a population parameter, so everything within that population was used in calculating that number. So when we say the mu of sub x, we say sub to represent the subscript here. The mu of sub x bar means the mean of all of the, remember x bar is also a symbol for mean. So this really means the mean of my means, those are all my sample means, is equal to the mean of the population. This is exactly what we saw on the previous slide. The mean of all of my sample means is equal to the mean of the population. And we can actually see this for every sample. Let's say that I list samples of size 3, and I list every single sample that I can pull for that population. Again, there's only one value that actually hit the mean of the population. But you'll also notice that we have less spread of our data. In one direction, the highest to the right, we go away from 80 is 1 inch, and the lowest we go away from 80 is 2.3 inches. And if we add up all these x bars and divide by 6, we see that the mean of all the means is equal to 80, which is the mean of the population. If we take it out to a sample size of 4, and we see, again, the mean of these means. Now in this case, we didn't even have a value that hit 80. However, we got pretty close, and there's that spread. We're still going to the right 1, but to the left we're only off by 1.5 now. So as my sample size is getting bigger, we're seeing less spread away from the mean, which should make sense because we're including more of the actual population values within our samples. And the mean of the means again is equal to 80. So for every sample size that I pulled, the mean of all the means was always equal to the population mean. Now, you'll notice again that here I've got almost a sample size that's almost equal to my population size. The population size was 5. This is a sample size 4. And also I want to note that any one of these individual samples was not equal to the mean of the population, except for in a couple of random cases. So, just like we had sort of established before, if we take a sample, one sample from a population, it's probably not going to equal the population number. However, as our samples get bigger, we get more and more accurate values. So let's lay out what the central limit theorem says. You're going to see some of the stuff we've already mentioned here. So let's start out. For any given population with a mean mu and standard deviation sigma, a sampling distribution, that's a table of values that we create with every single possible sample, with sample sizes of at least 30, will have the following three characteristics. Number one, the sampling distribution will approximate a normal distribution regardless of the original. We're going to come back to that point here in a minute, so let's just leave that one aside. The mean of sampling distribution equals the mean of the population. That's not to say that every sample within the distribution is equal to the mean of the population. However, if we were to find every single sample and take the mean of all of those means, it would equal the mean of the population. And then three, this is something that we saw, but we really didn't express verbally. And we're going to explore this part a little bit more. But the standard deviation of the sampling distribution, remember the standard deviation is the moving away from the middle, equals the standard deviation of the population divided by the square root of the sample size. See this actually in this formula here. And picture this x here as having a bar over the top. So really this is reading as sigma sub x bar, so the standard deviation of the table that I produced, which is my sampling distribution, equals the standard deviation of the population, but then divided by the square root of my sample size. To understand this a little bit, let's go back to a picture that looks at the distribution of the same numbers we were just examining. So the standard deviation is changing, decreases, as the sample size increases. Here's a picture of what we were just looking at, but graphically. We start out, number one, with the original population. These are my heights spread out over a x-axis. Then we took a sample of size 2. Remember, that gave us 10 different heights. And of course, they're also spread out along the axis here. But something happens as we get bigger and bigger samples. Notice how it's kind of like an upside down pyramid. These points begin to gather and gather closer and closer around the blue line. The blue line, of course, represents the mean. Notice that it doesn't matter what sample size I had, the mean remained consistent throughout. So the mean of the sampling distribution was always consistent no matter what the sample size was. The mean of all the means is equal to the population mean. However, the standard deviation of these distributions is not the same. The standard deviation actually decreases as our sample size increases. And we can also see it with the picture of our curve here. Here's our population, and then as we pull samples from that population, here our samples are size 4. So what we're looking at here is not the original data, but rather the different means that I pulled from the original population. So we gathered up samples of size 4, and we found the average of those samples. Well, as the samples get bigger, my results get more and more accurate to the middle here, which is 100. And so you can kind of picture the data gathering toward the center, pushing up the number of values that are close to the middle. And this change in standard deviation to our calculator, in fact, we saw the formula for it. For example, if the standard deviation of a population is 9, and remember when we say the population, we're referring to the original data, the x's. So, if the standard deviation of a population is 9, then we create a distribution of samples of size 100 from a population, what is the standard deviation of that sampling distribution? In other words, what is the deviation of those x bars around the mean? Picture again a table of samples of size 100 put into a table and what their mean was, and then we record their mean on the x-axis, horizontal axis. What happens to the standard deviation? Well, we can see if the original deviation was 9, and we have samples of size 100, if I divide 9 by the square root of 100, we get 9/10, which is 0.9. So we went from our data being spread out with an average of about 9 units from the mean on average. All the distances from the mean average out to about 9 units. When I take samples of 100, those samples of 100, and let's just say I do that 1,000 times, come out to have a standard deviation of 0.9 from the middle. So you can see that's a big difference, 9/10, which is less than 1, and 9 units from my original population. That's the picture that we have here. My standard deviation is decreasing. Here, each value, each mean, is about 4 units away from the middle of 100. Here, they're spread out with an average distance of 8. Here, they're spread out with an average distance of 16. So, as my sample gets bigger and I look at the distribution of those values, they get smaller. Let's go back also to the original things I was looking at. Notice how when I had samples of 3 versus 4, and we could even go to samples of size 2, the spread of these numbers are much closer to 80 as my samples get bigger. Again, we're only off by 80 to the right 1, and to the left 1.5, here to the left 2.3, and to the right 1. If we go back to my samples of size 2, we can see that we went as low as 3 from 80 and as high as 83.5, so we're 3 point off, 5 off on the right, 3 off on the left, so we had a range of 6.5. And then as our samples grow, here we have a range of 3.3, and here we have a range of 2.1. So as our samples increase, our values get more and more accurate, they get closer to the mean. Here's another example of this phenomenon. Based on the information from National Association of Theater Owners, the standard deviation of ticket prices is 0.72. If samples of size 52 are taken, what would the standard deviation of the sample distribution be? If we take 72 cents and we divide it by the square root of 52, we get 10 cents. So we went from having an average deviation of 72 cents to our samples of size 52 having an average standard deviation of 10 cents. So this distribution, when you work through some of the problems in the section starting out, they're going to ask you for standard error. And that's exactly what this is. Taking the standard deviation and dividing it by the square root of 52 gives us what we call, or at least some call, standard error. Let's look at the first part of the central limit theorem, which we didn't much touch on, but it said something about the original distribution being irrelevant, and that as long as we took sample sizes of at least 30, that the distribution of our means is approximately normal. Let's just start out with a population that is normal to begin with. So if we know that our original data has a normal distribution to begin with, you can see that no matter what size my sample is, whether it's 1, whether it's 2, whether it's 10, whether it's 30, the curve we get from that is also normal. So if we start out with a normal distribution, sample size is irrelevant, every sample from that will be normally distributed as well. But what's really interesting is that if I have any distribution, we've talked about skewed to the left, skewed to the right. We've talked about uniform distributions, etc. As we start to pull samples from these populations, right? And so here we start out with sample size 2. Well, once we've done that, we see that the distribution really is not normal. This one is definitely skewed to the right. This was triangular in nature. We saw this with random numbers that we added together, etc. But as my sample sizes increase, no matter what my original data was doing, the distribution of their means eventually becomes normal. In fact, we say this is approximately normal because most populations are not perfectly normal anyways. But this is good to know. This tells me that as long as I have a big enough sample, I don't really care how the original data was distributed. Once I get to 30, everything after that we can expect will fall into a normal distribution. This is probably the most powerful part of the central limit theorem, because it tells us that whenever we take samples from populations, we can expect that those samples will behave in a normal way, meaning a normal distribution, no matter what the original data, or however the original data was distributed. The central limit theorem tells us that normal distribution truly is normal. No matter, as soon as we get to at least 30, it's always approximately normal. And it's also important to keep in mind too that with data that we already know has a normal distribution, we know, for example, height already within a population has a normal distribution, and lots of other phenomena. With those, we don't even need to get to 30, when everything after that would be normal. So everything tends to center toward a distribution, no matter how it starts out, it will always eventually come to a normal distribution, and we're talking about the means of a population, once we get to samples of size 30 or more. So, as we're doing word problems, a couple of procedures that you want to follow and a couple things I want us to know that differ a little bit from what we were doing in the previous module. We're still going to use normal CDF on our calculators, etc. But let's go ahead and look at the steps we would want to follow. Number one, for every one of these problems where we're dealing with the normal curve, we always want to draw a picture and label it according to the parameters of our problem. Second, we're going to either use normal CDF if we're after an area, or invert norm if we're after a value along the horizontal axis on our calculators, matching what we're writing to the graph we have created. Note that for a sampling distribution, has a different standard deviation. Here it is. This is the standard deviation of a sampling distribution. And once we have found that area, or once we have found the value along the horizontal axis, we want to make sure we answer the question posed using complete sentences or phrases. If we're after the Z value of our data value, remember what that tells us for any individual value. We can use this translation formula that takes us from our data to what it would be in terms of standard deviations. It is modified slightly because we're talking about not just the X, a single data value from a population, but rather a set of values, a collection of values, a sample of values that we have found the mean of. If we subtract the mean of the sampling distribution, which is actually equal to the mean of the population, and divide it by, here's the big change, sigma sub x bar, which we know is different. Remember, sigma sub x bar, we take the original sigma, the original standard deviation of the population, we divide it by the square root of it. Okay, let's look at one more example of how we can use this to calculate probability, and how this will change slightly from what we did in the last section. So, if a population has a normal distribution, notice that with our original population having a normal distribution, it wouldn't really matter what sample sizes we have. But let's say that the mean of the population is 50 and the standard deviation of the population is 10. We intend to draw a sample of 100. It's obviously way bigger than the 30 we need. The question is, what is the probability that our sample mean that we draw from the population will be greater than 52? Well, the mean of the population is 50, so by selecting greater than 52, we're 2 off from the mean. We can calculate this probability using the normal CDF. So here, our probability that our mean that we pick from the population would be greater than 52. Here we would use normal CDF 52, 1000. So we're going to aim for just a very big infinity value. The mean of the population is 50, and here's normally where we would just put 10. But we don't put 10. We put 10 divided by the square root of 100, because the standard deviation has changed now that I'm taking a sample, not of one item, but of 100 items. We find that the population, or the probability, is about 2.28%. See if you can calculate the probability that the sample mean we draw from a population of 100 will be less than 48.5. Go ahead and pause. Here we have them all. Alright, for this one, sorry, I've got a little error there, but, and I'm noticing here the R was missing as well. Let's just go with it. Normal CDF, negative 1000, we're going to negative infinity on the left, all the way up to 48.5, my upper boundary, comma, mean of the standard, the population is 50, and 10 divided by the square root of 100 again. But we're in low probability for 0.668. Look at the last one. Normal CDF, we have two boundaries, 48.5 and 52. So that's our lower and upper boundary, 50. And we see this should not be 0.0668. This should actually be this 0.9104. This I hope gives you something to work with as you're starting to work in with the central limit theorem. As you go on to the next slideshow presentation, we're going to look more closely at some applications of this in some more real-world problems.